Okay, so in the last lecture, we defined what Schur processes are, and obviously I'll remind you some of this, but and we endowed them with some probabilistic meaning. And so what I'm going to be primarily after in this lecture is showing you at a, not in complete detail, but at some level of detail, how you can use the structure of the Schur process, in fact, the fact that it is a determinantal point process, in order to extract asymptotics in this scaling where you have many, many coordinates. So in particular, let me kind of set the stage. So if you'll recall, our Schur processes depended on parameters, collections of A's. I'll just kind of think of this as some arbitrary list, and B's. And I always assume that the AI BJs are all between 0 and 1. They could be 0. Okay. And the Schur process was then defined with respect to a choice of a downright path. And for the purpose of this lecture, you could imagine, for instance, one of two different choices of downright paths. I'll probably draw primarily in the first case, but so imagine, for instance, a downright path that was simply a zigzag. Okay, and so again, so you have at each one of these lattice points along the path, you have a partition. You have the empty partitions on the boundaries. And then the weight is given by the product of these skew Schur polynomials with parameters given by the A's or the B's corresponding to the labeling on the coordinate axes. Another nice example is to choose some m and some n, and then choose my path gamma to be the thing that just marches horizontal and then vertical. And in both of these cases, I can imagine taking, for instance, let me say m is equal to alpha times n. I could imagine taking n, which is this width in this case, to infinity. And when I do that, let me imagine I fix all of the A's and the B's, maybe fix them to be the same for that matter. Maybe I take A times B equals theta. I can ask what happens to my measure. Now, this seems a little abstract. It's a measure on an infinite number, on a growing number of partitions. How do you even visualize such a thing, let alone take a scaling limit? So maybe let me start by giving you just a way of visualizing this measure in what I would consider a more appealing way, which is really to visualize it in terms of non-intersecting paths. Okay, so let me describe that. To any partition, you can associate to it a shift where you take lambda 1 and you subtract 1 from it, lambda 2 and you subtract 2, lambda 3 and you subtract 3, and so on and so forth. Okay? Now the purpose of doing this shift is simply to separate points, right? A partition could be 4, 2, 2, 1, and if I'm going to imagine plotting these points at certain heights, I would have multiplicities. I have points on top of each other. So this shift will separate out. It becomes 3, 1, 0, and whatever this is supposed to be, minus 2, I guess, right? So it separates the points out under this mapping. In particular, the empty partition, which is all zeros, gets mapped to what I had kind of described as the step initial data, just the negative integers. Not complicated. Okay. So now what I want to imagine is plotting after doing this sort of affine shift. I want to plot the partitions, lambda super 1, lambda super 2, and so on and so forth. And what I'll imagine plotting is I have, lambda 1, lambda 2, lambda 3, and I'm going to plot above that. So I think of my horizontal index as the distance along gamma. And I think of the vertical, I plot my points. So I plot the number which would be lambda 1 minus 1. So that's the vertical height. And then I plot the point lambda 2 minus 2, and maybe lambda 3 minus 3, and so on and so forth. Okay? So that's the idea. Let me give you a worked out example. Okay? So let's consider, and I guess this is in maybe the second context. Let me consider the situation where my downright path goes to the right by 2 and then down by 2. Okay, so this is, the path looks like this. I have my lambda 1, lambda 2, and lambda 3, and then of course I append it by these empty partitions. And let's imagine that the configuration happens to assign, I choose a random configuration according to the Schur process, and let's say that it assigns me that lambda 1 is just 4, lambda 2 is the partition 5, 2, and lambda 3 is the partition 3. Of course, all zeros after that. Notation is clear? So let me plot this now. Okay. So I think of plotting again. Let me start with on the horizontal. So I have J. J I think of as my superscript. So of course this is empty and this is empty. So when J is 0, what I should think of is I take my shift of the empty partition. Okay, so I start off at minus 1, minus 2, minus 3, and I just put a dot at every point which I get by taking the shift of the empty partition. Okay? So I'm plotting the points at height minus 1, minus 2, minus 3, so on and so forth. So really, this goes on all the way down to infinity, so on and so forth. Fair? Now, for lambda 1, so I move over by 1, and now I plot the shift of this partition. And of course, all of the points except for the first one are the same, because I've appended myself with all zeros again. Except now the 4 gets shifted and it becomes, I guess, height 3. So this is 0, 1, 2, 4, so on and so forth. So I have something that's of height 3. Now, rather than just visualizing this as a bunch of points, I'm going to connect these, right? So I can connect all of these. And here I go half of the way, and then I take a step up, and I go over. Nothing complicated. And I do the same thing for partition 5, 2. So 5 gets shifted to 4. So I plot a point at height 4. 2 gets shifted. I subtract off 2 from that. So 2 gets shifted to 0. And when I draw my connection, it looks like this now. And then all these points just get shifted. Is it clear how this is going? And the final one, 3, gets shifted down to 2. And then everything else goes back down to this level. Okay, so it shifts down. This goes over and down. Everything else goes horizontal. And finally, I go back to the empty partition. And the empty partition forces me back down to this level. So I go over. OK, so is the picture clear? So now, when you look at this, you see actually what we're really dealing with is that the Schur process is a measure on non-intersecting, constant, I guess piecewise constant curves, which go up when I'm moving in the horizontal direction along my gamma, and go down when I move in the down direction along gamma. Okay, so it went up and then down and then down. You see the non-intersection condition, which is equivalent to this interlacing condition in the Schur polynomials, forces that these curves, you can only activate kind of, if you've gone in distance 2, you can only activate the first 2 curves. Everything else stays kind of stuck together, forced. Now, the perspective that we'll take in the next lecture tomorrow morning is that actually you can really think of the Schur process as a measure that's described by looking at independent geometric random walks with jump parameters given by these a's and b's, and the decision of whether you go up or down given by the choice of gamma. conditioned not to intersect. That is simply what the Schur process is. And that perspective of independent random walkers conditioned on non-intersection is actually a very powerful perspective. And that's the Gibbsian line ensemble perspective, which allows us to say quite a lot about scaling limits. So what we're going to do now is, of course, go and consider what happens when you have, a much, much larger type of picture, and what type of asymptotics one might want to get out, and what type of tools we can use in order to access that. So let me draw in a sort of very crude attempt. Let me try to draw a version of this picture for larger n. Okay, and actually, let me focus on this situation. There's something there's something a little annoying about this type of geometry, because there's this sort of sharp turn in gamma, so it introduces some lack of smoothness in the limit shape. But so let me focus on this choice of a sort of diagonal gamma. And so in that case, what the picture will correspond to is, rather than going up, 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 and then down, 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 you go up and then down, up and then down, up and then down, and so on and so forth. So here's the sort of very rough schematic picture, and don't hold me to this looking any much like it actually is. But you have this sort of infinite sea of the empty partition that you start out with, and then you're going to kind of end in the infinite sea of empty partitions. And there's no way I'm ever going to get these lines to line up, but forgive me. And then what happens is, in the first step, you could go up a certain amount, right? And the next guys stay flat, right? And then, because I'm assuming that my gamma is the sort of zigzag one, then the next step, this one actually goes down some amount. It could go down all the way to where it started, but maybe it won't by entropy. But the second one can actually get activated there. It just won't go quite as high up, and so on and so forth. So let me kind of imagine, rather than trying to actually draw that, let me just kind of draw these as squiggles, if you'll permit it. So you kind of have these sort of ups and downs, and the second one kind of goes up and down, and the third one takes a little while longer to get activated, and then it goes up and down. And you kind of have this process whereby you have this perturbation away from this infinite sea of nothingness, and the time it takes for you to perturb around that eventually is such that you don't even perturb. So once you're deep enough in, you're forced to still go flat, and so on and so forth. So if you look at this picture, is it clear why you eventually need to terminate, right? Because you have these non-intersection conditions. Each time you go up or down, you can at most activate one new curve. And so if you are, if your width is something like n, you can at most activate n of these. Okay? Now, what is it, the sort of thing that we're interested in? Well, the first, maybe I'll get some color. The first thing, if you imagine actually doing a simulation, a big simulation, which is not so hard to do, but I'm not going to do on a chalkboard, is that you can imagine there's some limit shape. You take n to infinity, and you ask, well, where does the top curve live? Okay, what does the top curve look like? And then there's also the question of kind of a limit shape for the unperturbed region. Right? There's a region where things are kind of not doing anything interesting, and then there's a region where they're doing something interesting. And you want to know what this looks like, what this sort of lens looks like. Another type of question that is very natural is to study the density. So, okay, the way I've drawn this is probably misleading. You should really imagine that there are many, many more curves in the middle. It's getting denser and denser as you go in. And these kind of are spreading out, right? By entropy considerations, the top curve has a lot of space to run into. It can really kind of expand, but the lower curves are kind of forced together. So another type of question that you're interested in is you take a slice and you look at the density of curves. In other words, this curve, there might be a lot of space in between it, a lot of lattice points. But once you get deeper, once you get all the way down into the bottom, the density of these curves is density 1. Every single integer is occupied by one of these curves. So you can ask, how does the density change from obviously density 0 when you go super high to density 1 when you go super low? Yep.
I'm not sure to get it, but shouldn't the maximum be IID? Because if it's IID, it should be like more than
You're saying the maximum of this height? Or
yeah.
why would it be IID?
I know, but if you do the stairs you're doing, it keeps going up, down, up, down, up, down. Why should it increase or?
Well, because, so the boundary condition is the empty partition, right? So it's something in the spirit of, you're conditioning these random walks on starting and ending at, the same position. You have this sort of barrier of infinite numbers of these flat random walks beneath. And so when you do that conditioning, it forces that in order to explore more of the phase space, you need to go up in the middle. And of course, it's hard to go up right near the edges because that's energetically very costly. It requires your random walks to kind of quickly go up. And geometric random walks don't like to jump up too quickly. But in the middle, you can go up much more because, well, you have a lot of steps and you can get this sort of displacement. Okay? So it's like saying if you take a Brownian motion and you condition it to be positive, between 0 and 1, or a Brownian bridge between 0 and 1, that it will kind of take a sort of shape, right? It will be smallest near 0 and 1, and it will be kind of biggest somewhere in the middle. So that's the sort of intuition for the nature of this. Yes?
Yeah, I have a related question. So is it always symmetric like this? Or can this top be moved, let's say, to the left or to the right?
Do you mean, is the picture always symmetric?
Yes.
So it's not, it's almost never symmetric in the sense of if I sample from the Sherp process, and I reflect it, I won't get the exact same picture. On the other hand, it's statistically symmetric because, well, if you remember back to the definition of the Sherp process, if I look at the process going this way versus this way, it's exactly the same law. So that's why one expects, at least at some law of large numbers level or some statistical level, that the limit shape should be symmetric. And moreover, you expect actually that there are kind of some additional symmetries in the nature of the fluctuations. Is that clear? Okay, these are great questions. Okay, so like I said, this is of course not very well drawn, but let me kind of continue just talking about potential questions of interest. So you see the density here is going to 1. It's kind of density here is going to 0. You might ask about something like the large deviations, the probability that the top curve is much higher than you expect it to be, or that the bottom perturbation is much lower than you expect it to be. You can ask questions, as we said, about the density profile. You could ask questions about local limit theorems. For instance, if I look somewhere in the bulk, I look at the point process of where these curves are crossing. I can ask, does that converge as n goes to infinity to something? I could ask the same thing along at the edge. In fact, I can ask spatial questions. I can ask, what if I look in some window around the edge? Do these collections of curves converge to something? And the answer to all these questions is yes, they do. And I'll give you the tools to understand what these objects are and how to get to them. Obviously, there are other questions you can ask about the sort of mesoscopic statistics or the sort of convergence of this process around its limit shape to a Gaussian free field. So there's a whole host of different and very interesting questions to consider. Okay, so what I'm going to be most interested in is the edge. And the reason is that, well, the motivating example that we've been talking about is last passage percolation. And we already learned that last passage percolation in law along a path gamma is equal to the top path, or the top of this collection of curves, of random curves. Right? So if I look at this, remember this is my lambda j 1 minus 1. this is essentially up to this shift by 1, the last passage percolation time, as I vary along my path gamma. So by studying the behavior of this object and its scaling properties, I can access the well, first of all, a limit theorem, law of large numbers, but then a fluctuation limit theorem for this. And so the type of result that we're going to, well, we won't prove all the way, but we'll at least kind of see the tools to prove, is that if I imagine taking n to infinity, then if I look in the vicinity of the edge of the limit shape, and I'll tell you where that limit shape lies, if I look in a vertical window of size n to the 1/3 and a horizontal window of size n to the 2/3, then there is a scaling limit as n goes to infinity to a collection of random curves that are somehow parabolically inclined, which is called the parabolic Airy line ensemble. And this is an object that is very important in the study of the KPZ universality class. So this collection of curves near the edge converges. Both converges, so what I'll talk about today is somehow the type of convergence where I look at a few slices, vertical slices, and I ask how the point process converges. But the convergence can be strengthened, and we'll talk about this tomorrow morning, to convergence in like the local uniform topology on curves. So a much stronger form of convergence. And with this in your pocket, you can prove a lot about the geometry of last passage percolation. Okay. So that's the sort of aim. Now it's a non-trivial process to get to there. Okay. And what I'm going to do in the rest of this lecture is kind of walk you in that direction. So what we will first do is restrict our attention to just a single slice of this picture. Okay? And what we'll look at is the point process that's formed by that slice. In other words, we'll look at the law of the marginal at some given point along my path gamma. We'll look at the marginal law of the Schur process. Okay? Now that marginal law has a name. It's called a Schur measure. And it's written in terms of objects that are slightly more complicated, but still not very complicated, than skew Schur polynomials, which are called Schur polynomials. So we'll introduce what are Schur polynomials, and we'll introduce a sort of fundamental property about them, which is that they have nice determinantal formulas. With that in hand, I'll introduce determinantal point processes and give you a sort of fundamental theorem about determinantal point processes, how they arise. And putting these two things together will show that the Schur measure is a determinantal point process. Now, there's a stronger result that I could have stated and proved that says that if I look at any finite number of slices and I look at the point processes, that is also determinantal. It's a little bit harder, and I won't prove that. Once we know that this is determinantal, so what is it going to mean to be determinantal? It's going to mean that the law of this point process is entirely captured by a single matrix, a single kernel that describes this. So it's almost as nice as a Poisson or a Bernoulli point process being captured by just knowing the intensity measure, but it's one degree more complicated. And once we have that tool in our hand, we can study the scaling limit through this determinantal kernel that will take a very nice form, and we can access this entire picture. Okay, so that's the sort of outline of where we're going. So let me proceed. I think I can erase most of this. Now, I won't go into all of the details of all of the things that I have said. And if you want to find more of the details, and I mentioned this in the appendix of the notes, I gave lectures last summer in Vancouver at the PIM summer school. And if you go to their website and you find my lecture notes, I mentioned, I go into much more detail on some of these things in, I think it was week 3, lecture 1, 2, and 3. But, okay. So let me define what are called multivariate Schur polynomials, or just Schur polynomials. It just means so Schur polynomials are indexed by partitions. In fact, you can have what are called multivariate skew Schur polynomials. Actually, let me, for the sake of argument, let me write that. So imagine I have two partitions, lambda and mu. Okay, and again, this means that lambda, this is the skew partition. So this thing will be 0 unless lambda contains mu. But now I'm going to consider this in multiple variables. So x1 through xn. So before we had a definition for this for just single variables, and now I'm going to define it for multi-variables. So this is defined as the summation. So I imagine that I have, I'll call it lambda naught is equal to lambda, and that this should intertwine with lambda 1 all the way down to lambda n, which should equal mu. So I'm going to sum over all sequences of these interlacing partitions, and then I'm going to put in here the skew Schur polynomial lambda 1 over lambda 0 in variable x1, lambda 2 over lambda 1 in variable x2, all the way up to lambda n over lambda n minus 1 in variable xn. Okay, this looks complicated, right? Like it's some gigantic sum. But if you think about it from the perspective of my Schur process, so remember I had lambda 1 up to lambda m, I guess, and then down to lambda m plus n minus 1, and the empty partition. If I look at the marginal, if I look, let's say I try to sum out, I have initially a measure on all of these partitions, but I can start to sum out some of these partitions and look at the marginal just on a subset of these. When I take that marginal, what it involves is it involves summing out these types of terms. Right? I would need to sum out, let's say I want to integrate out this term. So I would sum out over the variable lambda m minus 1, and I would have the product of two skew Schur polynomials, and that would give me a skew Schur polynomial in two variables, am and am minus 1. So this is sort of conflation. Now if I sum out over all of these variables, and let's say I also sum out over all of these variables, on this side, the definition of this skew multivariable Schur polynomial will tell me that the marginal, so the probability marginally on lambda m, will be equal to s lambda m in the variables a1 through am, and then s lambda m in the variables b1 through bn, and then of course with this normalization pi from before. Is that clear? We've just used the definition, which was this summing out over all these skew polynomials, to write down a formula in terms of whatever these objects are, these skew Schur polynomials. Now, this is something that's called the Schur measure. So the process is the multi-variable thing, and the measure is where you just look at a marginal on a single partition. Something that's a priori not obvious, but is not hard to show, is that these s lambdas, in these multivariable s lambdas, are symmetric polynomials in the variables. That's not at all clear from this definition, right? It doesn't look like they're interacting in any sort of symmetric way. But the claim is that if I look at, say, s lambda x1, x2, Now, this is the same as S lambda of x2, x1. Okay. Why is this true? Okay, I'll tell you in words one reason, and then in the last 2 lectures I'll give you a different proof using the Yang-Baxter equation. The most direct proof is that if you think about what this is saying from the perspective of this sort of picture here, okay? So this is saying that the Schur polynomial is given by starting with some polynomial mu, maybe the empty, if I write, just to be clear, when I write the mu is the empty partition, I just write this as lambda, okay? So that's how this S lambda is defined. So I start with some mu, maybe it's the empty partition. And then I look at the partition function. I look at the sum over all paths that end up at lambda. So maybe this state is lambda, and this state, whatever the point process is mu. And I look at the sum over all paths, and I weight those paths based on these, well, the x or the a parameters. These are these like geometric jump parameters, right, in the definition of skew-Schur polynomials. Well, that type of expression, which is looking at a partition function for non-intersecting paths, there's something called the Lingstrom-Gessel-Viennot lemma that says that such a thing will always be given as a determinant of the underlying point-to-point partition function. This is a combinatorial version of the Carlin-McGregor formula that you may be familiar with from things like Brownian motion. Right? If you look at 2 non-intersecting or 3 non-intersecting Brownian motions, conditioned to start and end in certain points, you can write the transition probabilities as a 3 by 3 determinant or an n by n determinant if you have such a thing. So there's a combinatorial version which is called the Lingstrom-Gessel-Viennot lemma. And what that implies is, in fact, that these Schur polynomials can be written as determinants of some sort of elementary symmetric polynomial, which is giving the point-to-point for a single path transition probability or transition weight. And because of that, and because of the symmetry of the point-to-point, right? If I take a geometric random walk that has, it jumps with parameter a1 in the first step and then parameter a2 in the second step, and I condition it to start and end at a given location, the sum over all potential middle points doesn't depend on the order of the a1 and the a2, right? So that symmetry of the one path weight implies that, in fact, these Schur polynomials, because it goes into the determinant, are themselves symmetric. Okay, so this is not a particularly hard proof. If you look up the Lingstrom-Gessel-Viennot lemma on Wikipedia, the only example they give of using it is to prove that the Schur polynomials are symmetric. Okay? So I won't go into that, and it's not a hard proof, so you can take a look there. Okay. Now, so we have that these are symmetric polynomials, and we've given what's called a combinatorial formula. This is sometimes also denoted, maybe you've seen these before. This is equivalent to a formula which is to write a Schur polynomial in terms of a sum over what are called Gelfand Zetlin patterns or a semi-standard Young tableau. Okay, so if you've seen such a thing, this is the exact same thing. Now, there's another formula that is very useful, and this goes back 100 years or so, 120 years, and this is called the Cauchy bialternate formula, and it gives an alternative formula for S lambda, right? So you see here this sort of combinatorial summation formula, but the Cauchy bialternate formula, which again is not terribly hard to prove, but it would take the better part of a lecture to go into the details. So I'll give it to you, and you can find the details sketched out in those Vancouver notes. It tells you that these Schur polynomials are actually written in terms of ratios of determinants. So let me just describe what this is. So this is called the Cauchy bialternate formula. Well, you know, along the way to prove this, you also use the Cauchy determinant formula. There are a lot of Cauchys we're going to be talking about today. We'll also use the Cauchy residue theorem a little bit later. And we had the Cauchy and the Littlewood identities earlier. Anyway, Cauchy was a good guy. So if you have a partition, lambda 1, lambda 2, up to lambda n, so let's assume it has n parts. And let me define something that I'll call delta. This is this sort of staircase partition all the way down to 1. Okay. I can write S lambda in the variables x1 to xn as the ratio of something I'll define in a moment, which is called the alternate of lambda plus delta in the variables x1 through xn, divided by the van der Waals determinant, which is given by a delta x1 to xn. Okay, so what is a mu x1 through xn is defined as the determinant of xi to the mu j, I and j equals 1 to n. This formula also is a special case of the Weil denominator formula, the bidimension formula, coming up in representation theory. But the, okay, so this alternate is a determinant. You see, if I plug in delta, which is the denominator, this gives you the van der Waals determinant, right? Everyone has seen, right? If you write this a delta x1 through xn, well, you have this nice formula, and of course it evaluates to the product of, okay, maybe I get the order of the I and the j wrong, but something like this, up to a sign that I may be getting wrong. Okay. So this is a very nice denominator. Of course, the numerator is slightly more complicated. Rather than just putting in this delta, you're offsetting it by the values of lambda. From this formula, is it obvious that this is even symmetric? How do you see that this S lambda? Let me kind of imagine that a priori we didn't know that this was a sure polynomial, so we didn't already know something about it. How would you know that this is symmetric? Yeah?
Because determinant is alternance, so the quotient of two determinants is something.
Exactly. If you interchange x1 and x2, because it's a determinant, you get a minus sign. But you get the same on top and bottom. Okay, so because of this antisymmetry, the ratio of these two things will be antisymmetric. How do you know that this is a polynomial? Right? A priori, we're dividing some determinant by, well, okay, some polynomial, but we might get a rational function, right? Not a polynomial. How do we know that this divides this? The what?
It does not explode.
It doesn't explode. Well, right. We know that the sort of we know that the top is of a higher degree than the bottom, and it has the same zeros as the bottom. So the ratio needs to be a polynomial. Okay? So it needs to be a symmetric polynomial. It doesn't need to be the same thing as what I wrote over there, though. So proving that these two formulas are equivalent is a little bit of legwork. The basic idea is really the following. So if I start by calling this thing S tilde, imagining that it's not the same as that, I can prove pretty easily that S tilde satisfies the Cauchy identity. So the Cauchy identity is the fact that this is a probability measure. So Cauchy identity says that if I sum S lambda in some set of variables A and S lambda in some other set of variables B, that I get this pi AB. Okay, so this is the Cauchy identity. And you can prove the same thing is true for the tildes. Proving that is really a matter of using the Cauchy determinant formula and I think you use the Cauchy-Binet theorem too. But that doesn't mean that these S lambdas and the S and the S tilde are the same yet. But you can then use some tools of symmetric function theory, in particular orthogonality relations, to prove that, in fact, if you know that this is true, then you know that the S and the S lambda are the same. And that's the details that you can see worked out in the other set notes. So let me take this as now a known fact, if you'll permit. And let me talk about how this is useful. So I guess I should erase this. I worked so hard on this. Okay. So what are some implications of this knowledge? So, for instance, and this is an exercise, you can use this formula to evaluate nice specialization. So, this is this is a general formula. But if I take the x's or the a's or whatever to be some nice values, you can work out formulas. So what I'd really like, for instance, if I imagine taking my homogeneous LPP model, I really want to consider the situation where all the a's and all the b's are the same. Right? That's maybe the most natural model that corresponds to the homogeneous LPP that we started yesterday morning talking about. But you see from this perspective, it's a little bit degenerate. If I take all of the x's to be the same, I'm dividing by, the determinant is 0, obviously. Both determinants are 0, and so 0 over 0, so I need to work a little bit hard to get this. So in the first part of the exercise, I ask that actually you kind of separate out the problem and you consider what happens if you put in a geometric specialization of the parameters. So what's the point of doing this? Well, it turns out that when you do this, it's actually much, much easier to evaluate this expression. Okay? It's much easier to evaluate this ratio, and you get the following compelling formula. So the product I less than j, again, n minus 1, and then q to the lambda I plus n minus I minus q to the lambda j plus n minus j over q to the n minus I minus q to the n minus j. So now from this perspective of this formula, it's actually pretty easy to take the limit of q goes to 1. Right? Oh, I should make a note, maybe it's not entirely obvious, but these s lambdas, these are homogeneous. So if I have s lambda in a parameter, let's say theta, so theta, okay, let me say a times theta, a1 times theta, a2 times theta, so on and so forth, I can factor out the theta, right? And I get that this is theta to the size of lambda, and then s lambda in the remaining a's. Okay, so I can factor out this sort of factor. This is, again, because if each one of these has the theta in it, then I get theta to the difference of these, and there's a telescoping that occurs, and so that's why it works. So in particular, if I want to deal with the homogeneous case, it suffices to consider s lambda in all ones, right? Because I could have just put a theta back in, or some parameter in by at the cost of a factor. So anyway, so when I take q goes to 1, I can now pretty easily compute the limit, because each one of these terms has a limit as q goes to 1. And the limit that the formula you get is this very nice formula. Okay. It's not so clear how you would get this formula directly from this. So with this formula now in mind, so of course you'll prove this, let me write down just this Schur measure a little bit more explicitly. In the case where all the a's and the b's, the product is say theta. Okay, this is again this homogeneous case. So in the homogeneous case, I assume ai equals times bj is identically equal to say theta, which I assume is less than 1. And let me assume that n is bigger than or equal to m, so that lambda I is identically 0 for I bigger than m. Okay, so I'm assuming, in my original picture, I'm assuming, I guess, now that that the height is bigger than the width, and that will force that the partition here has at most m non-zero entries. So it has length at most m. So all of the lambdas after m are going to be 0. So I can write now the probability measure under this Schur measure on lambda. And when I do that, I can use, again, I factor out my theta. So I have, okay, the normalization was this pi, and that becomes 1 minus theta to the mn. So this was the remnant of pi. Remember, pi was like the product of the 1 over 1 minus ai bj. And if ai bj is theta, then I have just 1 minus theta to the number of terms, which is m times n. I have theta to the size of lambda, which was I get by kind of factoring theta out of all the Schur polynomials. And then I'm left with this expression here, this type of expression here. And so if I write it explicitly, I get the product I less than j less than or equal to m of, let me use the coordinates x I is equal to lambda I minus I. So I do this shift, and I get xi minus xj over j minus I. And then I have some additional terms coming left over from xi plus. Okay. There are some terms once I get too large, once j gets too large, where this is just 0. And so basically what I'm getting here are the extra terms coming from the fact that some of these are 0, and these are the terms where both of them are potentially not 0. So I get this measure. And you should really, maybe I go write it as. So it's a measure on numbers x1 up to x m. Maybe I shouldn't use the x's because I used that notation. Okay, let me call these, I'll call them capital X's. Okay, so these capital X's are really like, when I had my picture of these curves, this was, I cut my curve and I look at the intersection points. These are the X's. So this is the point process of where my collection of non-intersecting geometric paths intersect with some axis in the middle. And you see that it has a very nice form. This is a van der Rohe determinant. Okay? And then it has some weight function associated to it. Sorry, there's a typo. This, I think this is squared. Yeah, this should be squared. Typo in the notes. Yeah, it's squared because I have the product of two Schur polynomials, right? So I have this term, and then I have the term, well, I have another term like that. So I have a van der Rohe squared, and then I have some weight function. You think of this is a weight function because you imagine, so now I want you to kind of think in the language of like random matrix theory or point processes. You have a collection of these random x's, x1 through xn. If I didn't have this term, I would just have each term sitting in some potential. So I would have just independent particles in some potential. But then I have this interaction that is saying that the particles are repulsing each other, like a van der Rohe squared. And so this is very much akin to, well, it's a discrete version of a random matrix ensemble. And in fact, through various limit transitions, this Schur measure will converge to various objects from random matrix theory. So this object itself has a name. This is called the Meixner ensemble. Meixner orthogonal polynomial ensemble. That's because one of the techniques to study this probability measure on points is through using orthogonal polynomials, in particular the Meixner orthogonal polynomials. This weight function has to do with a class of classical symmetric polynomials, orthogonal polynomials. Now let me, what my aim is to do some asymptotics, but just before that, let me familiarize you with this measure a little bit more and tell you that maybe you've seen some versions of this measure or some simple limits of this measure so that maybe it doesn't seem quite as complicated. So what are some things that I can do to this measure? First, any questions about this, notation, any of this stuff? Now, when there are no questions, it means everyone's lost. So if I take the Meixner ensemble, what do I have? What do I have in my disposal? I have one parameter. I have theta, and then, of course, I have m and n. So let me play a game. And let me take theta and take it really close to 1. Okay. So what does this mean in terms of last passage percolation? Well, if I take a geometric random variable with parameter theta, and now I take theta to be 1 minus epsilon, what does that look like? And I take epsilon to 0. What does that look like? You can just shout it out. Yeah.
Like an exponential of parameter 1 over 1 minus epsilon?
That's right. So if I look at this geometric and then I multiply it itself by epsilon, then this will converge, I believe, as epsilon goes to 0 to an exponential with rate 1. Right? Maybe. Hopefully. So with that in mind, if I look at my xi's, and I call epsilon, so the xi's which have something to do, at least x1 has something to do with the last passage time. So I expect that the last passage time is going to diverge like epsilon inverse because the weights are diverging like that. So I ought to multiply it by epsilon to bring it back down to earth. And so if I multiply the xi's by epsilon, I call this, I don't know, yi. And I substitute in now, and I write this as a measure on y's, and I take epsilon goes to 0, I converge to a measure in the y's, this epsilon to 0 limit. And now these y's you should really think of as living in the real line, or the positive reals. Okay, well, a priori they live in like an epsilon net, but the epsilon goes to 0. So you know, an epsilon times z. But so when epsilon goes to 0, you get a measure on y1 through ym, I guess. Is that right, m? Yeah, ym, which is proportional to, again, the van der Waals squared and then this weight factor simplifies a little bit. I don't know if you think exponentials are simpler, but and it looks like this. So of course I wrote proportional because I didn't keep track of the constants. And so a nice exercise is to, well, first of all, compute what the normalization of this is, right? I'm going to, if I integrate this expression over the positive reals to the nth power, I get some number. What is that? Well, a priori, if I just asked you to do that, to solve that problem, and you would kind of look at me like, But here we already know what the normalization is, right? That was the content of the Cauchy identity for Schur polynomials, right? Which was an easy thing to prove. Well, we proved it by knowing the skew Cauchy, and the skew Cauchy is something that is pretty easy when you get down to it to prove. So from this, you could exactly compute. Obviously, it involves some factorial things and some this and that, you can exactly compute the normalization here. The measure that you get has a name. It's called the Laguerre ensemble, or the Laguerre, the singular value of the Laguerre unitary ensemble. This is an ensemble that comes up, well, for one, it comes up from exponential last passage percolation, or related model of TASAP. It also comes up from random matrix theory. So this is representing the point process that you get by looking at the singular values of a complex sample covariance matrix, Gaussian sample covariance matrix. There's a further limit I'm not going to write the details of, but I think I leave it as an exercise for you to figure it out. If I imagine taking n to infinity with m fixed, if I take n to infinity and I fix m, this expression here can be, well, there's going to be a recentering and things of this sort. So you end up with a measure after some nice recentering and maybe even some nice scaling. You end up with a measure that's known as the Gaussian unitary ensemble, or the Hermite ensemble, where you have, why I told this squared, a Gaussian weight. This is maybe the simplest object that you see in random matrix theory. You should really think of this as you have a priori m independent Gaussians, but then you subject these to a penalization for having close values. Alternatively, you can think of this as, you have a parabola and you have an energy which is given by just where you lie in this parabola, but then you add to it a Coulomb type energy, if you write this in exponential form, some sort of Coulomb repulsion, and you ask how m points will configure themselves in this quadratic well. Okay. All of these coming as limits of the Schur measure. And then there are various other limits as well, and I ask you to think about some of these in the exercises. Okay, questions? Yeah.
For the exponential case, is there an analogous model for the non-intersecting random walks?
For the non-intersecting random, yes, great question. So, well, why don't you answer the question? Well, you start with non-intersecting geometric jump random walks, right? And then you apply a scaling whereby the size of those things become epsilon inverse. And then if you scale that whole picture down vertically by epsilon, the increments will become exponential. So this line ensemble, this collection of non-intersecting random walks, will become that of exponential jump, kind of still discrete time, but continuous in the vertical direction, exponential jump random walks. Yeah. And then if you take the limit, for instance, that will bring you to this object. So in this case, the limit ends up being related, the limit of this sort of line ensemble picture ends up being Dyson-Brownian motion. Okay, well, or in fact, the real limit becomes this sort of non-intersecting Brownian bridges, starting and ending at the same points. There are other limits that you can play with. For instance, just to mention, if rather than taking the parameter theta to 1, imagine taking the parameter theta to 0. So when you look at last passage percolation, right, you have geometrics. If the parameter of the geometric is going to 0, that means that the geometrics are very unusual. It's very unusual for them to be equal to anything but 0, right? So if I just fix m and n, and I take theta to 0, I get a big fat matrix of all zeros, which is not very interesting. But if, on the other hand, I take theta, let's say I call theta, I don't know, epsilon. If I take, now, maybe I'll call it epsilon squared. If I take m and n to behave like epsilon inverse, let's say epsilon inverse, now I have epsilon to the minus 2 geometrics, each of which has parameter epsilon squared. Anyone can anyone just tell me what you might expect to get as a limit of that matrix? Yeah?
Poisson process.
A Poisson point process, exactly, of in this case intensity 1, right? Because the chance that you have a particle at any location is basically 1 over epsilon squared, but you have epsilon squared locations. So you'll have a Poisson number of points and they'll be uniform at random. And of course, if I could have put in some, additional rate factor, I don't know, r, and so then I would end up with, a rate r squared, I guess, Poisson point process. So in that limit, when I take theta to 0, what I get is a Poisson point process of some intensity. I can choose the intensity however I want. And then my last passage problem is equivalent to just looking at the path from the bottom to the top, which eats up the most number of points. So I can kind of go over, I don't know, maybe I go this way, and this way, and this way. So I've eaten up 3 points. Maybe this is maximal in this case. This model of last passage percolation through a Poissonian field is intimately related to a question called Ulam's problem, also known as the longest increasing subsequence problem. And the way that it works is that if you have a Poisson point process, if you condition on there to be n points, then you can, from that point process, you can form a permutation by keeping track. So you label, maybe n is 4. So you label the points 1, 2, 3, 4, and then you see where they come out on the y-axis, and you label 1, 2, 3, 4, the order. And now you say 1 goes to 1, 2 goes to 4, 3 goes to 3, and 4 goes to 2. That's a permutation. And in fact, the Poisson point process conditioned on there to be n points produces a uniform permutation, uniform into the Haar measure. So what you get here, the observable, this longest path is equivalent to studying what's called the longest increasing subsequence of a random permutation. But it's just a Poissonized version. So you Poissonize the size of the permutation, and you get your longest increasing subsequence of this Poissonized permutation. And of course, you can take a limit of this formula, and you get something called the Poissonized Plancherel measure. And you can analyze this problem. And this is one of the routes to analyzing and solving this problem and studying asymptotics. Okay, so maybe I'll stop with these sort of degenerations. Hopefully, you are inspired to look at some of them. And what I want to do in the remaining bit of this talk is tell you how you go from a formula like this, a formula in this spirit, or maybe the more general formula that involves these alternants. Maybe I'll keep the inhomogeneities in the picture. How do I get to asymptotic analysis? What is one way? There are other routes, but what is one route to asymptotic analysis? Okay, maybe a quick side note, which is, you see everything in my lectures, everything is delicate, okay? These are delicate results in the sense that they rely on exact formulas. But the asymptotics that you get out of these results are supposed to be universal. Proving that they're universal is hard. In some cases, for instance, in random matrix theory, you can prove nice universality results. You can replace this type of this type of potential with an arbitrary potential. You can change the nature to some degree of the interaction, of this quadratic interaction. So there are nice universality results that you can play with. But the way that these universality results usually come about is they say that a large class of models behaves the same as each other. It doesn't tell you how they behave. So it's like if you proved the central limit theorem and you just said all finite variance sums of IID random variables behave the same. And that would be great, but it would be a little unfulfilling because you would say, well, what does it look like? Well, of course, in that case, you know that the Gaussian is somehow a fixed point. So you would already know that that they look like a Gaussian. But here, this gives you access to what are these sort of universal fixed points that maybe are not so a priori clear. Okay. So I'd like to talk about what are called determinantal point processes, because these are examples. Point processes. So it takes a little bit to get to this. So let me start with some definition. Okay. So a random, I'll assume simple, meaning 1 point per location. Simple point process on a state space, which I'll use this sort of, I don't know, I'll call it capital chi. I don't know if that's what it's actually. Which I'll think of as a countable or finite state space. So for instance, Z, or the numbers 1 through n or something like that. You can do this for much more arbitrary, much more complicated spaces, for R, for higher dimensional stuff. It gets a little bit more complicated when you have uncountable things. You need to deal with densities and stuff. So let me just restrict to countable. So a random simple point process is a probability measure on what's called the configuration space of capital chi, which is the set of 0, 1 to the chi. So in other words, I have chi, so maybe chi is the number line, C. And a configuration is just, I assign certain points I say have a particle and some points don't. So that's a configuration. It's a probability measure on this, and of course, because this is potentially infinite, I'm really talking about with respect to the sort of Borel sigma algebra that just keeps track of kind of how many particles are in finite windows, compact windows. So with respect to the Borel sigma algebra, which is generated by, so the x's in configuration, such that the number of particles in any compact set is n, as n varies in the natural numbers and a varies in all compact subsets of chi. Okay, what is being said here in words is that my measures, the sigma algebra with respect to which these are defined, basically knows the information of how many points are in any compact set. Right, because a priori, you have this in an infinite thing, so you might be worried, well, how do I define this when I go off to infinity? But really, when I'm talking about this simple point processes, I'm keeping track of the information, which is how many points are there in compact sets, for all compact sets. And so, okay, what are some examples? So here's an example. So let me define something. I'll call NA of X is for such a compact set. So it's this. So let me call this thing NA of X. This is the number of particles in the point process X that are in the window A. So I think of A as some window. Maybe A is this. And I just say, well, so NA is now 3 for this particular instance of X. So a very simple example is, let me just fix that I'm on Z, is to look at Bernoulli, say homogeneous Bernoulli row point process. So what is that? It's a product measure with probability rho that I have a particle at a given site. Of course, I could have some inhomogeneous measure, rho of X that depends on the location X. But anyway, in that case, NA of x is just equal to, it's distributed as a binomial with parameter rho of the size of A. And moreover, this point process is characterized by the fact that NA of x is independent of NB of x for A intersect B, which is empty. So this is exactly like, the Bernoulli point process is the discrete version of the Poisson point process. So this is like the characterization of the Poisson point process, right? Poisson number and then this independence in space. So a random simple point process is going to be completely characterized. This is an example. So a random point process is characterized completely by its correlation functions. So correlation functions are essentially what I've been talking about here. And these are defined as, for any window, any compact subset A, these are defined as the probability under this measure that A is contained in the set X. And this is for any A which is in capital Chi, which is finite. So kind of turning it around a little bit. So now what I want to do is I imagine I have my point process. Goes so on and so forth, and I choose some subset. Maybe the subset is these 3 points. I call that A, and I ask, what was the probability that these 3 points actually lied in the instance of my point process? So under this random measure on capital X. So again, for the Bernoulli, this is really easy. This would just be equal to rho to the size of A. Right? That's the probability you have that A points in that point process. But in general, the knowledge of this as A spans all finite subsets will characterize a random point process. In particular, since A is being assumed to be finite, we might as well think of A as equal to some collection of points, x1 up to xn for any given n. And then we introduce the notation of the endpoint correlation function rho n of x1 through xn. It's a symmetric function in these x's, and it's the probability that the set x1 through xn is in capital X, random according to this measure. Okay, so I haven't really done much. I've just set a bunch of notation. So the important So the definition of a determinantal point process, so we say a simple random point process is determinantal. And this is a word that is really annoying to write in emails because Google always corrects it, at least for me, to detrimental. Which maybe describes what happens when you pursue this area. But if there exists what's called a kernel or a matrix, it's basically a function from chi squared, so chi cross chi, to the reals or the complex or some field, such that for all n bigger than or equal to 1, and then all x1 through xn in chi distinct, the n-point correlation function at positions x1 through xn is equal to the determinant of k xi xj as I and j span from 1 to n. In which case k is called the correlation kernel. So the k is for correlation. No, the k is for kernel. But okay, so let's digest this just a little bit. So first of all, let's just work out what happens in this special example, this Bernoulli example. So in the Bernoulli example, I told you that rho n of x1 through xn, well, what's the probability that x1 through xn is in my random set? It was equal to rho to the n, right? Now, you can write this is kind of an odd way of writing this, but you can write this as the determinant of k xi xj, where k xy is equal to the diagonal matrix times rho on the diagonal. Sorry, that should be rho. Now, it's a diagonal matrix, so the determinant is just the product of the eigenvalue, the values on the diagonal, and so you get rho to the n. So this is a special case of a determinantal point process. You see, however, a determinantal, you could have also had a situation where you had an inhomogeneous Bernoulli point process, right, where the probability that you have a particle at position I is rho I, in which case this would be the product of rho x1 through rho xn, in which case you would just put rho xi here. So what's happening is you're going away from this sort of IID setting, or this independent setting, but you're just kind of adding one dimension of complexity, because you have the same matrix for any choice of x1 through xn and any n. So in a sense, this matrix really captures kind of two-point interactions, right? But it's giving you all higher interactions. It's giving you all higher correlation functions. So there's a lot of information in this K. In fact, everything is in this K. This is a massive reduction in complexity. Of course, you need to know whether there are any examples other than this. Maybe there are none. But luckily, there are many. In fact, there's kind of a general theory that says that under certain conditions on K, there will be a point process that corresponds to that. I'm not going to go that direction, but what I'll instead do is I'll talk about kind of a general class of random point processes that it will include the Schur measure that are determinantal, and I'll tell you how to get the fact that they're determinantal. Okay. One other kind of side comment is that K is not unique. The determinant, if I conjugate K, the determinant is unchanged. So there's, I can always conjugate the correlation kernel. So there's not a unique correlation kernel. It's unique up to conjugation, though. Okay, so what I'd like to get to is the statement that the Schur measure is determinantal. And then, well, if I have time, I can tell you a little bit about how you use that, but maybe I won't have time. And it really relies on the structure. So if you recall, the Schur measure let me think of it in terms of, so let me say, my capital X I call lambda 1 minus 1 and lambda 2 minus 2 and so on and so forth. So there was this expression using this Cauchy by alternate formula that the Schur measure on this set capital X, maybe with the arrow, is proportional to the, maybe I want to put in a plus n here. So it's proportional to to a product of determinants. So something like ai to the xj and then determinant of bi to the xj. And then, of course, there's normalization, right? This was the numerator in the Cauchy bialternate formula takes this form. So this was like my lambda plus n minus I type expression. The lambda plus the delta gives me these x's. So I have a particular form of my measure, and what I want to do is I want to argue that kind of general measures of this sort are determinantal and have a nice correlation kernel. So let me define what's called an n-particle biorthogonal ensemble. And these are the types of objects that come up a lot in random matrix theory and a lot also in this realm of probability. So these are, so is a probability measure, call it Pn, on sets x1 through xn in chi distinct. So it's an endpoint measure, distinct, with probability of this flavor. So let me write the more general thing. Pn of x1 through xn is equal to some normalization, and then the determinant of some function phi I of xj, ij1 to n, and then the determinant of chi I xj, ij equals 1 to n. So again, you should think of it, it's a measure on n points, distinct points, exactly like here, where the measure is proportional to the determinant of some function. Of course, here the function is that phi I is equal to ai to the argument, and the psi I is equal to bi to the argument. But this is a more general thing. And the only condition is such that phi I and psi I are functions from chi to the reals, and this pairing of psi I x phi j x summed over x is finite for all I and j in 1 through n. This has a name. We call this Gij. This is called the Gram matrix. So this is a very general class of probability measures. It will clearly include the class that we're interested in. And I'm going to state a theorem that says that this general class is determinantal. Before I do that, are there questions about the definition, the relation to the Schur measure, or any of this sort of stuff? Yeah.
It's just a notation question. If the n indexing the x
Yeah.
is the same that capital N under P?
Yeah, maybe I've been a little sloppy. I guess in the notation that I was using, maybe I was using capital M as opposed to capital N. When I choose my specializations, my AIs and BJs, you remember I had my rectangle, right? So I can choose one of the sides to be longer. Whichever one is the shorter size fixes the number of potentially non-zero entries in my partition. So I guess if I wanted this to be, so this, when I do this offset, eventually I just get to the sort of saturated situation, right? Where I've just offset 0, 0, 0, 0, 0, 0. So I'm really kind of keeping track of the non-trivial elements. So the first, I guess in this situation, the first m elements. So maybe what I wrote up here is an instance of like a PM in my notation from below. Yeah. But either way, you can think of this Schur measure either as a measure which kind of has this infinite support on points that are just packed together eventually, or you can think of it as a measure on the coordinates which could be non-trivial, in which case it's on a finite number of coordinates, and finite number of variables, and then it's exactly of this sort, maybe with m and n switched around. Okay. Other questions? Okay. So here's the theorem, and I won't prove it here. Again, you can see it in these other notes proved. It's, again, not a terribly hard proof. It basically relies on the Cauchy-Binet theorem. But it says that any n-point biorthogonal ensemble is determinantal with correlation kernel K that is very explicit. It's given by the sum ij equals 1 to n of phi I of x, psi j of y, and then the inverse of the transpose of this Gram matrix in the ij coordinate. Now, why is this thing called the biorthogonal ensemble? Imagine that these functions psi and phi were themselves biorthogonal. Now, that would mean that G, that this Gram matrix, is diagonal. And if G is diagonal, then its inverse transpose is very easy to compute. And all this is saying is that this correlation kernel is given by this pairing of the of these psi's and these i's in this manner. Okay. And in fact, you can always transform these into a biorthogonal form. And so this is really how you get the proof of this. And the transformation of how you get to the biorthogonal form is what produces this inverse of the Gram matrix. So that's the theorem. I won't prove it though. But let me just write down how this applies now to this case of the Schur measure. So again, by this, what I just wrote over there, by this bialternate formula, you have that the Schur measure takes exactly this form with particular choice of the psi and the phi. So psi I of x is ai to the x, and psi I of, y is bi to the y. Okay. Now, that tells you exactly what the kernel is for the Schur measure. So for the Schur measure, the Schur measure is determinantal, so it follows Schur measure is determinantal, and its correlation kernel, which I'll write as a k tilde for the moment, is given exactly by ai to the x, bj to the y. That's summed I equals 1 to n. I guess I'm assuming now that the sort of endpoint. So maybe I'm taking m is bigger than n, in which case I'm restricting, and I'm looking at the measure here. So I have an endpoint measure, and then this Gram matrix inverse transpose. And the Gram matrix is pretty simple. It's the sum, well, what is it? So it's the sum over all points in my space of this product. Now, under this transformation that I kind of butchered here, so let me write it better. So this is equal to lambda 1 plus n minus 1, lambda 2 plus n minus 2, and so on and so forth. Under this transformation, when I get to lambda n, which is the sort of last one who could be trivial, that one will be bigger than or equal to 0. So I can think of this point process as having a state space which is the non-negative integers, because I've added this shift by n. Okay? So when I do that, now I compute my gram matrix by summing over the coordinate in chi, which is to say L bigger than or equal to 0 of phi I L phi j L. So in other words, AI to the L, Bj to the L, which is nothing but 1 minus AI Bj inverse. So really this pi function from before. So in order to get this correlation kernel, I need to compute the ijth entry of the inverse transpose of this matrix. Okay. Now that might seem complicated, but this is like a pretty nice matrix. In fact, you can always compute the coordinates of the inverse of matrix using Cramer's formula. And so, or Cramer's rule. And what Cramer's rule tells you is that this is equal to something, some sign, and then the determinant of G where you've removed the ith row in the jth column divided by the determinant of G. Okay, this is how you compute the inverse, the coordinates of the inverse. Each one of these determinants is a Cauchy determinant. Okay, the Cauchy determinant, right, is the determinant of a matrix whose entries are of this form. And the Cauchy determinant formula, which I'm not going to write down, tells you that these determinants are products. And so the ratio of the determinant is a ratio of products. And so this gives you an explicit formula for these things, which you can see in the notes. It's just some products involving the A's and the B's. And so this gives you exactly what this correlation kernel is. Now, let's see how we are on time. Okay, so let me wrap up by kind of concluding the formula that you get here. So again, it's a summation of a bunch of stuff and then a bunch of products, and it looks kind of complicated. But with a little bit of massaging and a little bit of complex analysis, basically the Cauchy residue theorem, you can rewrite it in a final form, and that's where I'll kind of end. You can rewrite this kernel as 1 over 2 pi I squared, and then a double complex contour integral of, you might say, well, how is this any simpler than a sum 1 to n? But I'll tell you why in a moment. ZBM 1 minus VAM over Z minus AM, V minus BM, and then Z to the X, V to the Y over 1 minus ZV, dz dv, where these contours that you're integrating over need to be such, let me assume all the A's and the B's are somehow inside, and then 1 is here. So the contours somehow need to enclose all the residues but not enclose 1. So I won't get into the details of the contours, but the point is that this summation can be encapsulated in a way by this integration. What happens is basically as you shrink or deform your contours, you pick up residues, and each residue corresponds to a term in this summation. Why in the world do you want a formula in terms of complex contour integrals when you could have a formula in terms of summations? And so this is the last thing I'll say is, if I take n to infinity, this formula gets more and more complicated. Right? I have a summation over n and lots of terms, and I need to kind of keep track of all of the terms. When I've rewritten in terms of complex contour integrals, and for instance, if I imagine that the A's and the B's are all the same, let's say that AI and the a's and the b's are all equal to some q, you see that this expression takes the form of what you can basically write it in, if you write it in exponential form, you can write it as something like e to the n f of v minus f of w for some function f that's like involving the logarithms, right? Because you see the way z comes in is the 1 minus z times q and then z minus q, and then here it's flipped in the other way around. So you have something which is of the form of an integral or double integral of e to the n and then the difference of two functions, and then this is a very simple term that doesn't involve n. And as n goes to infinity, the analysis of this type of integral can be done through Laplace's method, through steepest descent methods, which I won't go into the details of. But once you have that in your hand, you can probe all of the types of asymptotics that I alluded to earlier. And maybe in the beginning of the next lecture, I'll say a little bit more about this before I dive into the content from the next lecture. But so hopefully I've gotten you to a point where you appreciate that these Schur measures not only are interesting, but that they have some structure that allows you to eventually take asymptotics with some considerable work. And we'll talk a little bit more about that in the next lecture. Okay, thank you.